to say the best implant is one that's forgotten by the body's biological systems, meaning if it can be a direct match for stiffness and therefore strain, or if it could ideally resorb over time, which I believe is going to be a reality in the next decade or so, then we solve the problem of this stiff, mismatched, solid piece of metal living that person's body for the rest of their life and causing issues. So, how do we do that? Can we maintain stiffness while strength increases? I think a big portion of it is to be able to start looking at implants as bespoke, personalized products. Anymore now, and if you go and buy something, you want something personal to you, right? Um, I want this with my initials on it. I want this color to match what I'm looking for. The problem is, we're still in implants, we're still doing a one size fits all, or a few hundred sizes that we happen to bring in a set has to fit this patient, the best fit. So the surgeons have to do a lot of sawing and trimming of the bone to get the implant to fit the way that they want it to. But I don't think that has to be the case. The other problem is that because of regulatory issues, we have to pass the FDA or other, the EU's MDR requirements. We end up having to test to absurd limits compared to a clinically relevant biomechanical load. Here's one of them. 40 times difference. And this is again, you pulling from direct or ortho load, concatenated data from research papers, versus a 50th percentile load required to pass the FDA's testing based on devices that have been cleared before. So we're talking about a 40x difference in strength and therefore stiffness, right? So how can we start to change the paradigm using 3D printing? So I'm going to take a little bit of a risk. It looks like I've used about 10 minutes to to do some live modeling. I love doing this. This is fun. So essentially, what we have here is we've got a humerus. This was a bone in my repository that I had available. So even though we're talking about hip implants, we're using a humerus just for an example's sake. So what you'll see here is essentially this is, we've got a bone and we've got a void that we need to fill. Now this void is most likely because of some sort of oncology related thing, some sort of tumor, some sort of resection that had to happen. Could be because of an accident, but we're just going to presume there's a section of bone that needs to match topology. What we can do now is we can essentially set up analysis, right? So we're going to set up essentially what this thing looks like, the strain distribution, when this bone is loaded in a certain condition. Because we know if it's intact, we know how the bone should act, the strains that should be present in the bone. Then we can essentially perform a simulation on the voided bone, right, with the issue. And we note its strain pattern. What we can do then, excuse me, is we can look at the various strains. And what we see here is that for intact bone, we can see when we load it in this manner, we're presuming this person's, lifting some weights, right? A 50-pound curl, essentially. They're in that deal range, right? 2,500 microstrain. However, when we account for the void, we now see that various portions of this have pushed into that overuse, where we're going to start seeing some issues. We also see that because of the distribution of stresses now, we're going to have some stresses which are falling below our ideal stress range. So how can we sort of change this? Well, again, utilizing computational design, we can basically take this field and we can look at the difference between intact, what it should look like, and what it doesn't look like. That allows us to create a targeted scaffold that not only matches the topology of the bone, but also matches the strain range of the bone. And we've got lots of dials and things that we can pull, right?